Okay, so let's have a quick look at the Socrative test of this morning. So, in the first three questions, we had to calculate more or less the same thing, which was the line integral on some curve of this vector field. So what is exactly the vector field we're talking about? So the vector field here we have is, so let's say it's some p and q, and according to what is written here, we have p of xy is equal to x, and q of xy is equal to x also. Okay, so what do we have? We have that the integral on gamma of p dx plus q dy, this is exactly what we have to compute. Okay, so how does it work? If we have a parametric description of gamma, that means that we can write x of t, y of t for some t in t0, capital T, let's say, beginning point and end point, that will be written as the integral from t0 to capital T of p of x of t, y of t times x prime of t plus q x of t, y of t times y prime of t dt. Okay, and if that first integral here that I wrote here is really some notation that says I want to compute the line integral of the vector field composed of p and q on the curve gamma, this thing that you've got here is really a very usual integral with respect to the variable t, okay, a one variable integral on the interval t0 capital T. Okay, so now let's see what we have here. In our case, and we're going to describe the x of t, y of t in the different cases that are given, we have that we're going to have the integral from t0 to capital T. P of xy is given by, that's the first thing we said, p of xy is x, so p of x of t, y of t is just going to be x of t times x prime of t plus q of xy, as we, again we said that q of xy was given by x, so we have that it's going to be x of, sorry, so we have x of t times y prime of t dt. Okay, and what we have next is just we have to describe then what is the x and x of t and y of t in the different cases. So first case, we have the segment joining the point, let's call that point 0a00 and the point b10. So what does it look like? It's, well, simply if you represent that in the Cartesian plane, so the curve that we're talking about is just a piece of a curve, well, a curve in the Cartesian plane, and so we're in two dimensions, so it's just that segment. Okay, so assuming that's 1 0, that was 0 0, so this is the curve I'm talking about, right? The blue segment here that joins the origin to that one. Right, so as we said, the hardest work is going to be describe this curve. So it's just, well, if you look at this, y is constantly equal to 0, so y of t is constantly equal to 0, y x of t goes from 0 to 1. So I can say it's going to be equal to t for t between 0 and 1. Okay, all right, so that's my gamma of t here. You know that we're going to need the x prime of t, which is, of course, equal to 1, and y prime of t equals to 0. So now I'm just substituting these results in this above integrals. So I get that this is equal to integral. So t0 and t, that's going to be from 0 to 1 of x of t, so that's going to be t, times x prime, so times 1, plus x of t, which is 1, t again, sorry, times y prime of t, which is, well, we said 0. dt. So in the end, what do I get? I have to do the integral between 0 and 1 of t dt, which of course you know it's 1 over 2 t squared between 0 and 1, and so that is 1 over 2. Okay, so we have 1 over 2 for the first answer. Second one, we're going to join now the point A 0, 0 and the point C 0, 1. Okay, so how do we describe it this time? So here, x of t is just going to stay constantly equal to 0. Y of t is going to be, well, going from 0 to 1. Okay, so we are joining it in that direction. Okay, so what do we get? And sorry, again, I can compute x prime of t is equal to 0, y prime of t is then equals to 1. So my integral is going to be integral from 0 to 1. So x is 0 times x prime, which is also 0, plus the q part is given by also x of t, so again 0, times y prime 1 dt, so of course this is going to be equal to 0. Okay, next one, I'm joining the points. Okay, so we are here, so sorry about this. We have now we have now, okay, so that's the Cartesian plane xy, and we want to join the point B with coordinates 1, 0 and the point D, well, with coordinates 1, 1. Okay, so that's going to be that segment and in that direction. So how are we going to describe this? This is just going to be x of t now is constantly equal to 1, and y of t is taking some values that are going to go from 0 to 1. Okay, so that x prime of t is 0 and y prime of t is 1. Okay, so what do I get? I get that I'm doing the integral between 0 and 1. X of t is going to be 1 times x prime 0 plus the q component is going to be y of t. Sorry, the q component is again still the same one, x of t. So this is 1 times y prime of t, which is 1 dt. So I just have the integral from 0 to 1 of 1 dt, which is equal to 1. Okay, and finally, I've got on this nice little curve, which is a closed curve. So let me write the important things we have here. So that's a closed curve. And I've got this vector field V, which is composed of P and Q, with P equal to Y and Q equals to X. So, okay, so what do we have? The first question actually that we need to answer is this vector field conservative? Why? Because if it is, you know that the line integral on a closed curve of conservative vector field is equal to 0. So that's something you have to remember. Integral of a conservative vector field on a closed curve is equal to 0. Okay, so for this vector field, we need to, let's do several things. Let's first find the domain of this vector field. The domain of this vector field is R2. Why? There is no forbidden values. It's defined for any items in R2. So this is what we can call a star domain because, well, there's no hole in it, okay? You can choose actually any point and reach any other point with a direct line that belongs to R2. That's just the nicest example of this, okay? So I won't have to wonder about the star domain property. But then, do we have a conservative vector field? So now we can use the property that we saw this morning. Let's try to do dp over dy and to do dq over dx. And if we have an equality, then we know that as we are included in a star domain, that we can call this vector field conservative. Okay, so dp over dy is just going to be, well, obviously it's 1, dq over dx here also it's 1, so we have an equality, so we can conclude that V is conservative, okay, on this star domain. So I can just directly say that the integral of on the closed curve of this vector field is going to be equal to 0. Okay. Maybe I should add a small word about that star domain, as several of you asked this morning. Okay. So this property here that I've listed here is, well, this is one corollary of another property which tells you that the line integral of a conservative vector field on a curve depends only on the values of the corresponding potential at the end of the curves. Okay, so for instance, let's look again at the previous one, which we saw is conservative. Okay, so example, my vector field again is going to be given by P of xy is equal to y and Q of xy is equal to x. Let's find the corresponding what is scalar potential, right? So I know that I've done my test. I know that there exists a scalar potential. Let's call that f, so, such that gradient of f is equal to v. So you know that df over dx then is equal to y, and df over dy is equal to x. That's what it means, okay? Right? So what is f? F is obviously going to be something like f of xy is obviously going to be x times y plus maybe something that depends only on y, h of y. And here I get that f of xy is going to be, well, obviously x times y plus obviously something that depends only on x. So let's use different things to have compatibility between those two uh, hypotheses, assumptions, well, necessity even. We need that those functions are equal to 0, actually. Okay, so the corresponding scalar potential f of xy is equal to x times y. I can add, of course, any pure constant. It doesn't really matter. But I can't add anything that depends only on y. Otherwise, that wouldn't give me that one, nor anything that depends only on x. Otherwise, I wouldn't get this one. Okay. So f of xy is equal to x times y plus eventually a pure constant, but we don't care about that for the moment. Right, so what does it mean? Let's do this description again, this calculation. That's important. I want you to be able to redo that. Okay, how does it go? You've got your curve given by x of t, y of t for t between t0 and capital and the final t, right? Whatever the notations you want to use. Then what do we have? We have that the integral on gamma of p dx plus q dy. Okay, so I'm using the same formula as before. That's just going to be the integral from t0 to capital T of p was actually equal to y of t, okay, and times, so we said x prime of t, plus then we have q, which was x of t, times y prime of t dt. Okay, so what do we have? Y of t, x prime of t, plus x of t, y prime of t. And I hope that it evokes you something very important. It's like uv prime plus u prime v. Okay, so that's exactly the derivative according to t of x of t times y of t. Okay, which is what we found earlier, that the scalar potential corresponding to my P and Q vector field is given by x times y. So if x and y depend on t, this is what I'm going to get. Okay, so in the end, I've just got the integral of the derivative, so you can just write it as x of t, y of t, t0 t, and that means you just get the value of your scalar potential, the difference of the values of your scalar potential at both ends. It doesn't matter what happened in between the beginning point x0, y0 and the end point. So if you have x of t0, y of t0, and the endpoint x of t, y of t, it could be go there as a straight line. Your curve gamma could be a straight line, or it could be something very complicated. It doesn't matter, as long the result of this is just going to be, sorry about this, the result of the line integral is just going to depend on the values of the corresponding scalar potential at both ends. Okay, so this is very, very, very important. When so the little thing we have to care about is that when you want to apply this property, so you see you need to check if the vector field is conservative. But it's not enough to apply this thing where you check that dp over dy is equal to dq over dx. That's an important part, okay? But that's not enough. You need one more property, which is that topological property, that you have the curve is included in a star domain for the vector field. Of course, a curve in itself, you can always include it in R2, and R2 is a star domain, but you have to relate that to the corresponding vector field. Okay, so the example that we tried, which was something like our counterexample, our favorite counterexample, was the one where we had v of xy was given by minus y divided by x2 plus y2 and x divided by x2 plus y2, okay? In that case, we had that the domain of this vector field was equal to R2 star. Okay, well, sorry, the name is also star, but it's not a star domain. R2 star, meaning that I'm considering any couples of R2 except from the 0, 0 point, okay? So I have to exclude, so that's, well, you can write it as R2 minus the point 0, 0, okay? Right? You exclude this point. But anything else is well defined. So that's the domain of V. And now when we consider the different curves that we have done, there was one curve which was that completed one like this, where you have some straight lines, then portion of a circle, and straight line, and again a circle. The thing is that this curve itself is included in a star domain, because we said that ortho star is not a star domain. But if we say this R2 minus a half line, okay, we must exclude 0, but if I exclude a half line, like sorry, this half line that I should use another color probably. So let's use minus this half line. So that's just going to be, how can I describe it? It's going to be all the points that are described as x is equal to 0 and y is negative. Okay. Okay, so R2 minus that half line, this is a star domain. Okay, so because, well, you see that if you relate to the definition, you can find many points such that they will be able to reach all of the points of that domain. Okay, so so that's a star domain, and our curve here is included in the star domain. Whereas in the second case, where we were considering, so let me redraw my axis, so I still must exclude this point. I was considering a simple circle. That's, okay, my second curve, the trigonometric circle, all right? The problem with that is that that curve is not included in a star domain. You can't make a star domain that contains this curve, right? You would need to exclude some point. Okay, you would need to exclude at least a half line. All right, so, and if you exclude a half line, okay, if you want to proceed as before, and you want to exclude, let's say, a half line like this, then you cut the curve, right? The curve is not closed anymore, right? Because it's well, you have to exclude one point, some points of the curve. So that can't, you can't find any star domain that contains the curve. Well, the idea of a star domain is that it doesn't have any holes in it. Okay, so as long as you've got a hole, and the hole can be just one point, then it's not going to work, right? But the thing is that it's related to the vector field you want to calculate, but to the curve, right, that you want to deal. If I had chosen another circle, which would be, I don't know, like this one here, no problem. No problem to calculate the circulation of that circle, and I would get 0 because this circle then would be included in a star domain. I can choose the half plane or whichever, like before, exclude half line. There I would have a circulation equal to 0. Okay, so well, that's it. A few more precisions to what we dealt with this morning. Okay, so we'll work a bit more on that on Thursday, Friday for the tutorials. Thank you very much. See you.